So this is going to be the first kind of practice exam little video I post. I'm going to skip the first few because I think it's a little bit easier material. I'll try to get one made for those first few problems here tomorrow or Friday, but I want to focus on things I think are a little bit harder. So the first thing that we'll do is go to this practice exam A. I'm going to start on problem 5. Okay, so we've got this information given to us. We have two events, being Republican, not being Republican, wanting marijuana legalized nationally or not. Right? So we have this contingency table. We have one part left out. Right? So how can we find this missing value for X? Recall that we went through and said if we didn't have the totals, the way we found the totals were using these intersections. We could add across the rows or down the columns here. So, if I just want the probability somebody wants marijuana legalized, I'd add up all the Republicans who want it legalized and add to that all the non-Republicans who want it legalized. That would give me every single person that wants it legalized. So I can add across the row here. So I know that 0.15 plus X, oops, I switched over to mine there, plus X will be equal to 0.55 here. So I can do a little bit of algebra here, rearrange some things so that I know that X would be equal to 0.55 minus that 0.15, right? Which should give me that value of 0.4. And that makes sense. If I add 0.15 and 0.4, that gets me to that 0.5. So that one shouldn't be too bad. If I had left off one of these totals, so let's say I had something like this and I wanted you to solve for Z, you would simply add down the columns, 0.15 plus 0.35. So just kind of 0.15 plus 0.35 would give you Z there, or that total that we had in there before, which was originally 0.5. Okay? So the next question is asking, what's the probability an individual wants marijuana legalized given that they are a Republican? So here we can go to our formula sheet over here, I believe on the right hand side, and we've got some of our rules or probabilities. So we want a conditional probability, which we know that we can write as the intersection of these two events divided by whatever we're conditioning on. So I would have this formula sheet in front of me. I'll just copy and paste it here so we can have everything kind of on one line. And I'm just going to write this out in the context of my example. So the probability that I want is that someone wants marijuana legalized given or conditioned on that they're Republican. So my event A is, we'll call this legalized, which I think I set up here, is LM. And then conditional on if they're Republican, which we can call just R. Right? So this would be the intersection of those two events. So LM, actually I'm going to copy this so I don't have to kind of find it, given R. Right? And just to make this look a little prettier, I'll kind of get the formatting to be the same here. All right? We then would divide by whatever we're conditioning on, which here, what we're conditioning on is on the right-hand side of this vertical line. So we're conditioning on the fact that they are Republican. Okay. And now it's just a matter of entering those values in, right? So the probability of LM, or wanting marijuana legalized and being Republican, is just the intersection, which these top four cells represent our intersections. So marijuana legalized and Republican, that would be 0.15. Divided by the probability that someone is Republican, that's what our totals represent. So the probability someone is Republican is 0.5, and that should give us the answer of 0.3. Okay? The next one we have is, what is the probability that an individual is not a Republican and does not want marijuana legalized? Well, here, this is an intersection, right? This and represents an intersection. So if we wrote this out, what we're really saying is we want the probability that someone is not Republican. So we could say, call this LM and then complement. So let's go, just make this an equation. And then we'll add this here. So LM complement, right? And then we'll add in this and sign, right? The symbol for the and sign being, oh, actually it should allow me, I want to go to, oh, I want this to be, so where's the equation at? There we go. So here's my and sign, and does not want marijuana legalized and is not a Republican. I guess I wrote these in the opposite order, which it doesn't matter because it's an intersection. So I could have put this in here as they're not Republican or R complement and does not want marijuana legalized, LM complement. This is just an intersection, so go to not Republican, does not want marijuana legalized. It's simply that 0.1. Okay? So there, I can find the intersection pretty easily. It's just one of the values that are in that table. Okay? The next question I have is, are being Republican and wanting marijuana legalized, are they independent events? So if we look here, we've got some special conditions, and the one that represents independence is this one right here. So there's two checks we can do for independence. The first is we can check to see if this holds. So I'll go ahead and I'll do that first. So is the probability that wanting marijuana legalized, LM, and being a Republican, so I'll just write an and here, or I could have copy and pasted this intersection sign, and being a Republican, is that simply equal to the probability of each one of those events multiplied by each other? I don't know why, it must be a shorthand, right? So I can check that, right? Is the probability of LM and R, so wanting marijuana legalized and being Republican, so it's 0.15. If that is equal to the probability of wanting marijuana legalized, which here's wanting marijuana legalized, 0.55, times the probability of being Republican, which is just 0.5. Right? If those two values are the same, then we would say they're independent events. Now the problem is, right, this is actually, these two things aren't equal. Right? So if I go here, I'll put in these aren't the same, so not independent events. And I can't spell independent. Right? So that's not one of my justifications why, but I at least know from there that no, these can't be independent. So the second definition of independence we had was, is the probability of A given B, right? If that's just the same as the probability of A, so if the conditional probability of A, so we're still looking for the probability of A here, we've just conditioned on event B, excuse me. If that's the same as the unconditional probability of A, we would say these are independent events. Well, we don't have A and B here, right? We have LM and R. But what we want to make sure it holds is, because we could also have said it this way, right? Let me delete a line here so I can keep this all on the same page. We could have also said if the conditional probability of B is equal to the unconditional probability of B, then those events would be independent as well. It doesn't matter, which one of those holds. So we can think about what our event A would be. So that would be being Republican. Our event B here is wanting marijuana legalized. So here, where I have A and B, I'm just going to write R and LM. And if that's not the same as just the unconditional probability of R, right, I'm just plugging my events in here for A and B, then they won't be independent. Now we checked that in a different way, but how can I find a conditional probability? Well, this goes back to the multiplication rule. We can check to see whether or not that conditional probability, which we know is equal to this equation, is the same as the unconditional. So I'll just do this check here. We already had that up here to find that conditional probability of LM and R, but now we're going to find the conditional probability of R given LM. Right? So it'll just be the intersection of those two events. So actually, sorry, I wrote these backwards. R given LM is what we wanted to check. So I know that would be equal to the probability of the intersection of the two divided by the probability of what we condition on, which is LM here. Okay. So the intersection of R and LM, so yes, Republican, yes, they want it legalized, is 0.15 divided by the condition, or dividing by what we're conditioning on, which is the probability they want marijuana legalized, which is 0.55. Right? And I believe, let me double check here, kind of the intermediate values now. So 0.15 divided by 0.55 is about 0.27. If that's the same as just the unconditional probability of R, then they would be independent. If they're not the same, they're not independent. So we go up here, what's the probability of being Republican? So Republican is just 0.5. So 0.5 is not equal to 0.27. So these two probabilities aren't the same, and we would say no, they're not independent events. Okay. Now we could have checked it the other way as well. That wasn't one of the options given up here. But if we would have checked it and found that, say, the conditional probability of LM wasn't the same as the unconditional, we would know that if we check it one way, they have to be independent if we checked it the other way as well, or vice versa. If we found they're not independent, they wouldn't be independent if we checked it kind of using the other ways. So that's how you can check for independence there. You want to make sure that whatever's on the left-hand side here, that's what you're looking for the probability of. So like here, this doesn't make any sense. I'm saying, is the conditional probability of R not equal to the unconditional probability of LM? No, I want to be comparing the same events there. And that's why the answer there should be B. Okay? If I then wanted to check to see are they mutually exclusive, this is a real easy check. It's if the intersection of the two events is equal to 0, they are mutually exclusive. So if the intersection is equal to 0, that means they can't happen at the same time. They're mutually exclusive events. If the intersection was 0, we would have to have a 0 up here in one of these top 4 left cells. If we look at these events specifically, being Republican and wanting marijuana legalized, that probability is 0.15. It's not 0. So because it's not 0, they aren't mutually exclusive. The only way that they're mutually exclusive is if that intersection is equal to 0. So the answer here is no, they're not mutually exclusive, and it's because the intersection, which is written with that kind of upside down U, or that upside down set symbol, is not equal to 0. Right? So check for mutually exclusive is pretty easy. You just check to see if the intersection is equal to 0. If it is, they're mutually exclusive. If it's not 0, right, or it's not equal to 0 here, they wouldn't be mutually exclusive. All right, we'll do one more here, which is that I have kind of this nice little Venn diagram. It shows where A and B overlap. It gives me some different pieces of information. Now, what I know is that what's in these two circles plus what's outside of them, which I'm told is the intersection of the complements, or this kind of light blue area, when I add those together, it fills up the entire experimental outcome space, so I know those two things have to add to 1. So if I take that light blue area and I add to that what's in the circles, now I know what's in the area of these circles is it's in either A or it's in B. Said differently, that's the probability of A, and I'll use this U for right now. I'm going to change it here real quick. It would be A, I'll go to my design here, union B, or it's in A or it's in B. So those two areas will add to 1. From there, well, I don't directly have the union, but I know if I look at my formula sheet that I can simply rewrite the union right here of two events as the probability of both events add together and then subtract out the intersection. So I subtract out the intersection because when I added the probability of A to the probability of B, I double counted what was in between. So I can just plug that equation in and say, so not plugging anything in for this, but I know that the union can be rewritten as the probability of A plus the probability of B, and then I'm going to subtract the intersection of those two things. Okay? And I know those, because I'm just substituting in there an equation for the union, those have to add up to 1. And now it's just a matter of plugging values in, right? I've got, oops, the intersection of the complements, I'm told, is 0.2. So 0.2. Add to that the probability of A, which is told to me to be 0.5. Add to that the probability of B, which is what I don't know. And then subtract what I double counted, which is this intersection of 0.1. All those things have to add up to 1. And at this point, it's just a little bit of algebra to solve for what B is. So 0.2 plus 0.5 minus 0.1 is what? 0.6. So I add, kind of subtract 0.6 from both sides, and I'm left with that the probability of B would then be 0.4. Okay. So these were just kind of 6 questions here, all related to probability. I'll get the next video posted sometime tomorrow.